morning everyone. So today, the last class we talked about all one sample tests. So now we will move on to two samples. As I said, one sample, two samples, then we talk about many samples. Okay. So one random variable we now know to do hypothesis testing. Okay. Now moving on, we are going to do statistical inference for two samples. What do I mean by that? Two random variables basically. We are talking about two random variables instead of just one random variable, and of course with assumptions. Okay. So first let us take a simpler case. I have not talked about correlation formally defined, we have not defined formally correlation or multivariate random variables, right. We will define it after this portion. Okay. So here again we are going to assume that the two population is independent. Okay. The moment it becomes dependent, then things become different. Okay. So that will be the next step. Right now we will first assume the two populations are independent, and then we wanted to perform hypothesis testing. Okay. So again the assumption is x1 to xn is from random from a sample from population 1, x21 to x21, okay, and the two populations represented by x1 and x2 are independent. That means there is no commonality between them, no correlation between them, and both the populations are normal. Okay. That is a very important assumption. Okay. That tells you that the popularity of these methods is restricted, or the usability of these methods is restricted, not so popular, because again you have to assume that the underlying population itself is normal. Okay. Central limit, we are not taking support of central limit theorem, but we are assuming directly that the underlying population is normal. Under these conditions we can do both what I call population test for mean, test for variance, and test for what I call proportions. All three we can do. In this class we will quickly cover all these three. Okay. As I said, for one sample I took long time, for two samples I will take only one class. This class we will cover all these three ideas. Okay. Test hypothesis testing. So we are going to typically talk about expectation of x1 minus x2, that is difference in two population means. So am I saying, is this population, is this population better than the other one, is x1 population mean greater or less than x2 population. So typically happens when you compare drugs, when you compare effectiveness of drugs, how do you say one is better over the other? It is comparisons, and that is when this comes into picture. You understand, when this kind of hypothesis testing, when you are comparing drug efficiency, you are benchmarking one against the other. Why do you propose a new drug when already something is there? Either in terms of cost benefit, or in terms of side effects, or in terms of efficiency, right. That is the need for new drug development, right. What else? One could be, I want to develop it at a lower cost keeping the same benefits, or I may develop it as a higher cost but I will have more benefits. That is what we do, right. So then we are always comparing, and when we start comparing, that is when you have this comparison with another benchmark or another sample, another population. That is why we have x1 bar and x2 bar representing sample means from populations, is an estimate of mu1 and mu2. So we have mu1 minus mu2. So the hypothesis is in what? The null hypothesis is going to be on what? Mu1 minus mu2. Remember, the null hypothesis and alternate hypothesis is always about the truth. Okay. So null hypothesis is on mu1 minus mu2, and alternate, you could have it simply mu1 minus mu2 equal to 0, and alternate hypothesis could be mu1 minus mu2 greater than or equal to 0, or less than or equal to 0, or not equal to 0, greater than 0, less than 0, not equal to 0. Equal to 0 is your null hypothesis. So what is variance of x1 bar plus x1 minus x2? It is variance of x plus variance of y minus 2 times that is covariance, we will call it later. So you would have expectation of, so if you notice we have derived it in the class, expectation of variance of x plus y. How do I define? Or variance of x minus y, what do we do? If you do it, this is nothing but expectation of x plus y minus mu x, this is a minus b the whole square, right. When you do this, then you would be having, okay, so you would have expectation of x plus y the whole square plus mu x plus mu y the whole square minus 2 into x plus y into mu x plus, right. Then you could, this we derived in the class, right. So you would have something like variance of x plus variance of y plus 2 times expectation of x minus mu x into y minus mu y. This is what you would have had. And when it is, or you would have like this, if I expand it, this will be variance of x plus variance of y plus 2 times expectation of xy minus mu x mu y. Okay, this term will go to 0 because when they are independent, expectation of xy equals to expectation of x into expectation of y, because probability of A intersection B when they are independent is what? Probability of A into probability of B. That is the same idea, this will go to 0. Now when you have variance of x1 minus x2, what do you have? It is nothing but, since they are independent, it is going to be variance of x1 bar plus variance of x2 bar. Okay, if you take variance of x minus y, if you expand this, this will be variance of x plus variance of y minus 2 times so this variance of x1 bar plus x2 bar is nothing but sigma 1 squared by n plus sigma 2 squared by n. This is my variance. Okay. Now the same idea, what is the test statistic? We can use standard normal test statistic. Why? Because our assumption is what? The underlying population itself is normal. We have made an assumption that the underlying population itself is normal, and therefore what is the assumption, what is the test we could do? Standard normal test, which is nothing but x minus mu by sigma. In this case this is x bar minus mu by sigma over root n. Now this x bar itself will become x1 bar minus x2 bar minus mu 1 minus mu 2 divided by square root of sigma 1 by root n or sigma squared by n1 plus, that is the test statistic. So the numerator is x bar minus x minus mu, which is x bar minus mu, the denominator is the variance of x1 bar minus x2 bar is what we should know. That we can derive it, I have derived it in the class earlier. Okay, for x plus y, x minus y you can derive it the same way. Since you are assuming independency, this term goes to 0, so you will have only variance of x plus variance of y. So as I said, you can have now the null hypothesis, alternate hypothesis. The key is to derive the test statistic. Once you have derived the test statistic, it is straightforward. You just have null hypothesis is delta naught, whatever you want to have, alternate hypothesis greater than not equal to delta naught, greater than delta naught, less than delta naught, you will accordingly form the confidence intervals. Confidence intervals is also now known, right, because once you know the once you know the test statistic, what is the confidence interval? Mu minus mu will lie between x1 minus x2 plus or minus z alpha by 2 into sigma over root n. In this case is nothing but sigma is what? Square root of sigma 1 squared over n1 plus sigma 2 square by n2, that is all. You can directly write the, so it is just an extension. Instead of mu 1 we have mu 1 minus mu 2 lying between x bar plus or minus z alpha by 2 into sigma over root n. You simply replace x bar with x1 bar minus x2 bar plus or minus z alpha by 2 into square root of sigma 1 square by n1 plus sigma 2 square by n2. I have given a problem here that you can work out, because these are standard substitution of numbers basically, okay. And now you can again choose sample size. I think I have asked one of the problem to be sample size selection in quiz 1, the same idea, it is same. Now you instead of sigma 1 squared, you will have sigma 1 squared plus sigma 2 squared, okay. Straightforward extensions. Huh? N1 and N2 are equal. They are different, then you will have to have trouble, because your sample size for your sample size, then it becomes a combination, right. The problem is you are asking for one sample size which will reduce my error. Let us say I want to be 95% confident that the error is within, or x bar mu1 minus mu2 is within the limits. So you are asking for a sample size. So n1 plus n2 should be equal to n, that is all, okay. Now how do you increase n1, decrease n2, all of them will become problem. It will not be a straightforward answer if n1 and n2 are not equal. So that is why you assume n1 equals to n2, because only then you will say equal distribution, equal amount of data is there for sample 1, sample 2, so there is no skewness. But if you have skewness in the data, that is you have 90% of data for n1 is 90 and n2 is 10, then this will not work out, then biases has to be accounted for, you understand, right, because the data is more available for n1, that is population 1, and population 2 you have taken a very less sample. This is the classic issue in fault diagnosis or image recognition etc., where you take faces of all faces of guys and train the network. How will it detect a girl's face if there is very less data, right. That is why I assume for sample size n1 equals to n2, okay. So typically we will not know the mean variance, so we replace variance with what, instead of we replace standard deviation with what do we do, yes, right, sigma we replace with s square, okay. In this case also we are going to do the same, we do what is called as a pooled estimator, okay, which is a simplified one, okay. So now remember the challenge with this is what, the challenge with this, so this has sigma squared by n1 plus sigma squared by n2, that is nothing but sigma squared into 1 over n1 plus 1 over n2, okay. So assuming what is the assumption here, sigma 1 squared equals to sigma 2 squared, that is if you assume both the population have, so there are multiple cases, okay. The first case is when both the population variances are same, when both the population variances are same, so you take sigma squared as common and you have sigma squared divided by into 1 over n1 plus 1 over n2. So now the sigma square has to be replaced with s square. So I have s1 square and s2 square, s1 square is sigma 1 square, s2 square is sigma 2 square is a estimate of sigma 2 square, and I am combining to form what is known a pool estimator, which is sigma square. This is a case where the underlying variances of two populations are equal, or you have assumed it to be equal, then you create what is known as a pooled estimator. This is what a pooled estimator is. How did I get this? How did I get pooled estimator? Any idea? So the total degrees of freedom is what? The total degrees of freedom is what? n1 plus n2 minus 2. For each variance I calculate mean. So n1 plus n2 minus 2 is the one. So this is the total variance in n1, this is the total variability in n2 with degrees of freedom, and I divided by the total degree to get a pooled estimate. You understand how did I get this formula? So typically you have what, x1 squared equals to x1 minus mu the whole square by n1 minus 1. The total variability is what? N1 minus 1 into S1 squared, and similarly the total variability in the population is what? X2 minus mu the whole square divided by N2 minus 1. So, X2 minus mu the whole square is what? S2 square into N2 minus 1, and now the total degrees of freedom is what? N1 plus N2 minus 1. So, that is why I have S1 square into N1 minus 1, variability, total change in first population with regard to the mean, deviation in first population with regard to mean, deviation in the second population with regard to mean, divided by the total degrees of freedom. This is a pooled variance. What is x1 minus mu the whole square? The total deviation, square deviation in population 1 with regard to the mean. X2 minus mu the whole square, mu to the whole square is what? Total deviation in the population where with regard to mean. Okay. Now I divide the total deviation divided by the degrees of freedom, that is what is variances. Okay. So the numerator is the total deviation in the total two populations, the denominator is the total degrees of freedom. Clear? Make sense? So this is what a pooled estimator is. Once I have the pooled estimator, okay, I can replace that with the pooled estimator. You take sigma 1 squared outside, that is SP square becomes SP, which is the standard deviation, into square root of 1 by N1 plus 1 by N2. The total degrees of freedom is N1 plus N2 minus 2 degrees of freedom. Okay. For small population it will follow T distribution, for larger population T will converge to normal. So you may wonder why all of a sudden T distribution is coming into picture. T distribution will come into picture because it is N1 plus N2 minus 2. If it is less than 30 it will be T distribution, if it is greater than 30 it will become a normal central Gaussian distribution, that is all. It is a T distribution with degrees of freedom what? N1 plus N2 minus 2. If N1 plus N2 minus 2 is greater than 30 it automatically becomes a normal distribution. So this is a T distribution with N1 plus N2 minus 2 degrees of freedom, but typically N1 plus N2 minus 2 will be greater than 30, that means even if you do not collect 10 samples, what is it? 15 samples, right. So if you collect more than 15 samples in each group it automatically becomes a normal distribution, because T distribution greater than 30 is normal. So the underlying population is normal, okay, and the first case you are assuming both the variances are same, then you have what is called as a pooled estimator and you had a test. The other one is naturally what? When sigma 1 square not equals to sigma 2 square. In this case you do not have any clue, so you simply replace it with S1 square divided by N1 plus S2 square divided by N2. Okay. The catch here, as we were pointing out, if the catch here is the two variances are different, okay, it is not the same, and therefore it is a T distribution, okay, this is still T distribution but with a complicated degrees of freedom, it is not a straightforward degrees of freedom. You understand? The earlier case it was easy, the degrees of freedom is N1 plus N2 minus 2, because the total degrees of freedom, because both the population are same variance, it became N1 plus N2 minus 2. In this case both the populations will have different variances and that has to be accounted for while you are calculating the degrees of freedom, and that is why it comes up with a complicated formula. If you look at it, this is the total variance, total deviation divided by appropriate degrees of freedom, etc. Okay. So this becomes complicated. Okay. Usually this will also become central distribution, normal distribution if you take more than 30 samples. Okay. So that is the difference between assuming the underlying population variance to be same and population variance to be different. If you assume the population variance is same, the idea becomes simple, okay, degrees of freedom becomes simple. If you assume that the underlying populations have different variance, then the degrees of freedom become quite complicated, because it has to be account the variability in the population distributions. Okay. So, this is 2 sample, okay, different variances, and we have covered 2 sample equal variances, and both of them are T distributions. The underlying is normal distribution, population is normal, the test statistic is T distribution, and of course T distribution will become normal when you take more number of samples. That is what it is. Clear?